Hi, welcome to the Shuko Math Practice Lab. And this is our second video. We are talking about how to approximate a function by using the Taylor polynomial. And in the first practice, we covered two functions, exponential function and sine and cosine trig functions. So for the first video, we did the exponential function, how to approximate our exponential functions by using the Taylor polynomial, and we can center the polynomial at the different values, and they both can approximate the function values here. So today we're going to do our second video. In the second practice, we're going to take a look how can I practice. So right now, how about I want to estimate a cosine functions here. So the second videos here, we're going to talk about how do I approximate the value for the cosine 0.8 here. Okay, and now let's go ahead get started. And just like we did for the first video, now this is the one we are going to approximate the cosine 0.8. Okay, so remember the radius of the convergence is here for the cosine is infinity. So basically, if you want to approximate 0.8, you can just directly put into the value of the x, right? But today we're going to also show you can center at a different values. And then you still can approximate. Then we're going to talk about the pros and the cons for them. Okay, so let me first write down what is the cosine x, the Taylor polynomial expansion about the center at 0. So here is the polynomial, so it's 1, then this is x4, the 4 factorial, and the minus x6, the 6 factorial, plus x to the 8, a factorial, and the minus da 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 da. And this is the polynomial we centered at zeros here, all right? So the first thing is we want to approximate the 0.8. We just want to use the Taylor polynomial center at 0. And let's just, we can, so this is the method number 1. We just want to center at 0. And then we can just directly plug in our number. So for example, the cosine 0.8. So the problem asks us to use the first 4 non-zero terms here, all right? So I'm just going to show you. Okay, so the first one's here. Let's just use the 2 terms. So it's 1 minus, this is 0.8. You can just plug in directly to the 2. This is 2 factorials, right? So this one's here, I'm going to get 0.68. Now, I can also approximate it by using 3 terms. So it will be 1 minus 0.8 to the square to the 2 factorial plus 0.8 to the 4 factorial. So these numbers here will give us, you put it into the calculator, will be 697,0666. Now I also can use the 4 terms to the 6, right? So it's 0.8. So this will be 1 minus 2 factorial 0.8 to the square plus 4 factorial 0.8 to the 4th minus 0.8 to the 6 factorials, right? All right, so this one's here, if you plug in the calculator, you will get 0.69. Okay, so here, I need to be careful here. This one's 0.69, all right? So this is 0.6970. Okay, so this one is 0.6967025778. All right. Also, in here, if if we put the cosine point A, make sure you're in the radians mode, right? So the cosine point A, it will be 0.6967067,093. Okay, so this is the true value. Now, if I use the estimate here, let's take a look. If I use only two terms, what is my error going to be? So my error will just be 0.68 minus 0.6967, right? So my error going to be 0.0167067. It's pretty good, you know. It's very close to the second decimal point. That's pretty good. So the second one's here, the arrow, you just use 697066 minus the cosine 0.8. And then this one's here, the arrow will be 0.00035995. Wow, so this one's here, I only use three terms. It's already close to what? Fourth decimal point. That's pretty good estimation. Okay, so now take a look at if I use the four terms, the arrows here, this one will be point, okay, 0, 1, 2, 3, 4, 5. 1, 2, 3, 5, 4, 1, 3, 1, 1, 5. Wow, so that means my zero term is almost is to the what? 1, 2, 3, 4, 5 to the e to the negative 5s, right? So it's very, very good here, right? Okay, so now let's take a look at what is my bound here to see the bound agree or not. Okay, so because I use the first fourth terms, right? So let's take a look. So what is my next terms here? Next term is eighths, right? Okay, so now remember that. So we have the bound here will be what? So the f to the fourth eighth. Okay, so f to the eighth derivative. All right, so f to the eighth derivative of x. Okay, so let's see here, the f of the eighth derivatives, right? So I know this is so it will be what? It will be cosines here, right? So it will be the absolute value of cosines here, okay? And now where is my x here? Because I am centered at where? I'm centered at 0. I have a 0.8, right? So my x here will be from 0, right? So from 0 to what? 0 to 0.8. So what is the cosine value? Will have the maximus here. So the cosine will have the, let's say here, so the cosine is decreasing functions, right? So the cosine 0 has the maximum, correct? And the cosine 0 equal to what? Equal to 1. So we can say the m is equal to 1. So remember that we use this, we need to, we use this to find the m, right? And now I can put into what? I can put into the Lagrange error bound. So the arrow, so Rn going to be less than m. So what is the m's here? Is 1s, right? And then is a factorials here. Then in here will be x minus a, right? So x minus a, and my center is 0. So will be the point what? Point a minus 0 to the how many power? 8 powers, right? So now if you put these ones here, you will find this is a 0.0000504161. All right. Wow, look here. All right, so this is the arrow up bound, right? So this is the upper bound. That means that is the maximum error can here. So if you say, okay, how good it is, look here. This is the four terms, right? The true zeros here is 4, 1, 4, 1, 3, what? 4, 1, 3, 1, 5, right? So the true zeros here is 4, 1, 3, 1, 5. Okay, sorry, I kind of erase that. So it's a 4, 1, 3, 1, 5, right? So it is accurate to 4 ones here, 4, 1. Then this digit is here, right? So this one's here, this is 6, and this is 3. So yes, that's true. The true arrows here is less than the upper bound. So this is the highest arrow we can get by using this approximations, right? So center at the zeros here. Okay, now you said, how about, can we do a different center? Okay, let's try to take a look here, right? So this is the one. So how about, you said cosine? Okay, so 0.8. Okay, so if you take a look, pi over 4, if you put a pi equal to the 3.14, so pi over 4 is very close to what is the value? Is 0.78539, right? 539A1 something. And the 0.8, the one we want to estimate, the 0.8, is pretty close to the pi over 4, correct? So let's say, can we expand a function called the polynomial center at pi over 4? Can we do that? Of course, right? So that you can do the Taylor expansions, now let's take a look. What will be, all right, so what will be the function if I center at different places here? So here, let's see here. This is 0, 1, 2, 3, 4. This is my functions, right? So this is the derivative of my function. So the derivative is we still want to center at to estimate cosine 0.8. Can I do that? Well, of course. Then let's see how accurate it is one. So the first one, this is cosine x. Okay, so the next one is negative sine x. So this is negative cosine x, and this is a positive sine x. Then this is cosine x, right? Okay, now in here, this is interested here because now I am going to center the pi over 4. So my A is pi over 4. So I put a pi over 4 here. So you put a pi over 4 to the cosine is square root of 2 over 2. This is negative square root of 2 over 2, negative square root of the 2 over 2, square root of the 2 over 2, square root of the 2 over 2. Okay, so now let's try to write my expansions here. So the cosine x here, it will be the square root of the 2 over 2 f0s, right? Then plus, you take the first derivative here, right? So plus what? Plus you're going to have a negative square root of the 2 over 2 divided by 1. And then this is what? X minus pi over 4, right? Because you want to center at pi over 4. Then the next one is minus here, square root of 2 over 2. Then you have 2 factorials, right? Then you have x minus pi over 4 to the square. Then now this one here, you have a plus 3 factorial. All right, so then this one is the square root of the 2 over 2. Then this is x minus pi over 4 to the third power. Then plus here, right? Be careful, here's plus. So it's the square root of the 2 over 2 to the fourth factorial, x minus pi over 4 to the fourth dot, 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 dot. Okay, so as you see, the problem wanted us to do by using the first four non-zero term. That means this four, right? Then also you see they all have a constants. So I can take the constants square root of 2 over 2 out. So this will just be 1 minus x minus pi over 4. Then minus 2 factorial. Then this is x minus pi over 4 to the square. Then you say plus 3 factorial. And then this is x minus pi over 4 to the third. Then plus 4 factorial. And this is x minus pi over 4 to the fourth, dot, 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 right? Okay, so now since the problem asks us to find the first four, right? So these are my first four terms here. So let's do just like what we did before, see how accurate. Okay, so the cosine 0.8 can be approximated by the first two terms. So it will be the square root of the 2 over 2, 1 minus 0.8 minus pi over 4. Okay, so now in here, you will get, this one here is a 0.6967, 817, 817235. Wow. Okay, so let's also write down here, what is my true cosine value? True cosine 0.8 is equal to 0.6967, 0.67093. All right, so this is the first term. Or you can say the cosine 0.8, I can approximately by using one more term. So this will be 1 minus 0.8 minus pi over 4, then minus 1 over factorial x minus, so this is a pointer. So this is a pointer a minus pi over 4 to the square, right? So you add one more terms here. And these terms here will give you 0.6967, 0.63411. All right, so now I'm using the four terms as the problem want us. So it's square root of the 2 over 2. Then this is 1 minus 0.8 minus pi over 4 minus 1 over 2 square, 2 factorial minus pi over 4 square. Then plus 1 over 3 factorial pointer a minus pi over 4 to the third. Okay, so now let's see here. So this number is 0.6967, 0.098. Wow. Okay. Now, just like we did before, let's see the arrows here. If I only use two terms, what is the arrow? That means use 6967 minus the cosine 08. So the first one's here. So this one is a pointer 0, 0, 0. Oh, wow. Even 0.0007514. Oh my gosh, look here. You only use two terms. The arrow is to the fifth decimal point, right? Compared to if you use the center at 0, if you use the first term, there's only the arrow is only have the second decimal. And now if you are center, if you use the polynomial center at pi over 4, wow, the first two terms, the linear term, will be doing pretty good estimations, right? That's amazing. All right, so now the second one's here. Let's find this one's here. This is the arrow. Just use 697 minus cosine. Look here, this one will be 0.0000. So let me see, 1, 2, 3, 4, 5, 6. 60, and 36a, 24. Wow, this is e to the what? E to the -7th, right? So it's like to the 10 to the -7 terms. Wow, the estimation is extremely good. So the last one's here. So the last one, so I will use this number to minus cosine. So the arrows for the last one, it will be 1.3354, 1.33546 times 10 to the what? 10 to the -9. Wow, that's amazing. So if you compare to here, so this arrow is only to how many? 1, 2, 3, 4, 5, 6, 10 to the -6. And here the arrow is narrow to the 10 to the -9. Well, that's no surprise, right? Because this is just like we did for the exponentials here. So in here is 0, right? So you want to estimate 0.8. So you want to estimate 0.8. If you center from 0, this is how far away, right? So if you center from 0, this is how far away. But if you center for pi over 4, so we say the pi over 4 is 0.78, so it's here, right? So if you center pi over 4, it's very close to 0.8. So this is how far away you want to estimate where is the center. So no surprise. Of course, if you center at pi over 4, it's way faster to converge to the true values here, because that's what happens here, right? Okay, so now let's take a look the arrow terms here. Okay, so be careful here. So we want to do the first 4 now. So what happened here? So the next term is 4th, right? So it's 4 factorial, right? So it's 4 factorial. So that's why I will say the f of the 4th derivative of x. The f of the 4th derivative is what? Is cosine x. Am I right? Okay, so cosine x, then the x right now is from the pi over 4 to what? 0.8. And the cosine is a decreasing function. So that means the cosine the pi over 4 has what? Has the maximum value. So let's have our m's here. So cosine pi over 4 is square root of the 2 over 2. Right, so now my arrow bound, my Lagrange arrow bound will be m is what? Square root of the 2 over 2. Then the bottom is 4 factorial. Then here is x minus, right? So x is 0.8 minus pi over 4 to the how many powers? 4th powers, right? So if you put it into the calculator, and this one will give you 1.33937967965 to the 10 to the -9. Wow, look here. This is the maxima allowed, right? So see here. This is 1.33. So this third decimal 5, yeah, is less than the maxima here. So we know we did the calculation correctly. So here, right? So if you use the first 4 terms, then the maxima arrow by using the first 4 term is 1.3393 to the 10 to the -9. And this is a true arrow. Yes, it's less than that. So we know this is the what? So we know this is the upper bound, right? So this is the upper bound. All right, so that's what I say, when you do the approximation, so for these 3 functions, the radius of convergence is to the infinity, right? So it's infinity. So you can do just like what we did here. You just plug in. So the converge will be a little bit slower, and eventually it will, you still will be able to find the value of the cosine. Or if you are try to find the polynomial center at some other point, the point you know about the value. And so like for this example, I noticed the point 8 is very similar to the pi over 4. Then I can center at the pi over 4. All right, so you will see if you center at the pi over 4, the convergence to the true value is see here very close. Even just the linear is already what is like to the 5th decimal point. That's amazing, right? And the problems here, just like we did before, so you need to redo, you need to redo your like a Taylor series here, right? So find the new parameters, and then in here, the square root of the 2 over 2, in the older time without the calculator, square root of the 2 is very difficult to find its values here. So that's why, that's the problems here. If you don't have the calculator, square root of the 2 probably is not easy to find the value. So that's the pros and the cons for the, you use the different centers here. All right, so that's it. And so I hope for these 2 videos, you will get the ideas, what polynomial I need to use, where I centered. All right, you can center it at 0, or you can center it at other places here. It depends what is your value you want to. If you are centered at the value you want to find closely, then the convergence will be a lot faster. But then the same problem, you might run into the calculation problem, like the square root of the 2, and for the exponential function, we have the e. So they are all kind of a little bit difficult to do, right? So, but that's the pros and the cons. As you can see, if I center at the pi over 4, wow, the conversion to the true value, that's just extremely fast. All right, that's it. And I hope you get a good understanding for this polynomial approximation. Then we're going to talk about how about, the radius of convergence has a fixed number. Like if, for example, it's less than 1 or it's 1, then how do we choose the numbers here? All right. Okay, sounds good. I'll talk to you in our next videos. Okay, and bye.